This is the second part of the Chapter 2 lesson on the chemical context of life. Last time we talked about the structure of atoms and defined what neutrons, protons, and electrons were regarding their locations and also their charge. We focus mostly on protons and neutrons, and today we're going to look at the electrons, which are the negative charge. And again, they're not part of the nucleus. They are around the nucleus and what can be represented as like a cloud. But to simplify the electrons, their relative locations and numbers, we're going to be looking at drawings like the one on the right that shows two electrons that kind of stay in this general area around the nucleus for helium. But we do want to broaden our view of this and look at more of the elements from the periodic table, and also a trend that exists with electrons. Notice that across the top of each column, there's group 1A, group 2A. I'm going to hop over to group 3A, 4A, 5A, 6A, 7A, 8A. Those groups are arranged by their numbers of electrons in their outermost shell, if you will, which think of the shells as being like the general area where those electrons might be at any point in time. Hydrogen and helium have only one shell. Hydrogen has one electron in that shell to balance out the positive charge of its single proton. So when we're doing the drawings of the atomic structures, there will always be the same number of protons and electrons when that atom has a neutral charge. If it's in what's called an ion, then you'll see it might have a positive or a negative charge. But for now, know that the numbers of protons and the electrons have to be equal. So recall helium, as shown in the top right here, has an atomic number of 2, or 2 protons. So it's going to have also 2 electrons. The first shell can hold a maximum of 2 electrons. That's one of the rules that we have to follow about drawing the atomic structures of the elements. The first shell can hold up to 2. So it's only going to be hydrogen and helium that have only that first shell. Now that first shell in those cases is also known as the valence shell, which is the outermost shell of electrons, which are going to influence the behavior of the atom, how it can interact with other atoms in its environment. When we go down to the second row, we can see here that all of those elements have 2 valence shells, or 2 shells, rather 2 electron shells or orbitals. Only one of them is the valence. I apologize for misspeaking there. The valence would be the outermost shell. So lithium, for example, with an atomic number of 3 has 3 electrons. 2 can fit in the first shell, and that leaves 1 for the outer shell. So lithium has 1 valence electron, we would say. In contrast to, let's go to the other side. In group 8, we have neon with 10 protons based on its atomic number shown here before Ne. That little 10 means the atomic number, so it's going to have 10 electrons. 2 in the first shell, and that leaves 8 for the outer shell or the valence shell. So neon has 8 valence electrons. Remember that that last row, or column rather, is group 8. So looking at the group number is actually a hint about how many valence electrons it has. All of those elements in group 8 have 8 valence electrons, and in fact those are the inert elements or noble gases. They're not reactive because they already have a full valence of electrons, which means then the opposite is true for the rest of them. Lithium through fluorine, without having a full valence of 8 electrons, are reactive. How will they react? Well, that's where we'll go with the bonding soon. Before we get there, though, take a look at the third shell. The third row, which all of them have 3 shells. From sodium to argon, there are 3 shells of electrons, and sodium having 11 protons would have 11 electrons. You can go ahead and check the math there. 2 in the first, up to 8 in the second, so that brings us to 10. There's one more, and that goes in the third shell, which would be the valence shell, so that means that sodium has 1 valence electron. Let me go over to chlorine. So this is group 7, has 17 protons. It's going to have 17 electrons. 2 go in the first, so we have 15 left. 8 can go in the second, so there's 7 left. And you can check there's 7 valence electrons. It's group 7. Okay, so hopefully that hint will help you at least to check your work. I do want you to be able to draw structures like this. And in addition to showing the electrons in their orbitals, I would also like you to know the numbers and locations of the protons and the neutrons. So in the gray circle, the nucleus, you could draw, for example, for hydrogen, you would put 1 proton or 1 plus and 1 neutron or 1 N. So try to do that as an exercise, and we'll have some probably in class to practice as well. Now there's another trend that we can notice on the periodic table for the electrons. If you look at it now from the, well, actually I already mentioned that. So from the row perspective, just to recap then, the first row has 1 shell for electrons to be within. The second row has 2 shells. The third row has 3 shells. And then if you look at it from the group perspective, you go down the columns, they each have 1 valence electron. Group 2 has 2 valence electrons, and so forth. I hope that makes sense. Now we're going to take a look at how the locations and numbers of those electrons influences their reaction, the reactability of the atoms through bonding, chemical bonding. We're going to talk about 3 types of chemical bonds. The first we'll do is ionic bonds. Ionic bonds occur when there's a transfer of valence electrons between atoms. As shown here, we have sodium and chlorine. Now, something I mentioned on the previous mini lesson, the introduction to chapter 2, was that there is an importance to know the difference between like a metal and a nonmetal, and here's where that comes into play. Sodium is a metal, chlorine is a nonmetal. And I know that because if I go back to the periodic table and I look at the color coding, although the key's not shown here in your textbook, there would be a legend or a key above this that shows that the blue are the metals, the yellow are the nonmetals. So ionic bonds can only form between metals and nonmetals. That's one of the criteria. So we have metal and nonmetal. Another criteria is the compatibility of those atoms, of those different elements. Notice that sodium has 1 valence electron. It's not stable. Elements don't want just 1 valence electron. They want to have a full shell of 8 on their outermost orbital or valence shell, while chlorine has 7. So chlorine wants 1 more. Sodium wants to get rid of 1. So it's a perfect match. You have your metal and your nonmetal, and you have a metal who is looking to give away 1 electron and a nonmetal that's looking to receive 1 electron. This is how ionic bonds form. As a result, these form an ionic compound called sodium chloride. Sodium chloride is a type of salt. Salts are the result of ionic compounds, or salts are ionic compounds. Now, this is also how ions form. If the salt was to be dissolved, let's say, into a solution, the sodium and the chlorine would now become ions. Sodium has now 8 valence electrons, but it lost an electron. So because it lost an electron, it's actually now more positive in its charge. Okay, process that for a minute. So if it gave up an electron, it gave up something a little bit negative, it's going to be slightly more positive now. So that is why sodium has a plus with it. And anytime you have an ion with a positive charge, it's going to be called a cation. Versus chlorine, it's gaining more negative charge from that additional electron. It becomes an anion, a negatively charged ion. Our next type of bond is a covalent bond. Now, it's similar to the ionic bonds in one way. You're still looking at the compatibility of these different atoms based on their valence electrons and whether or not they have a full valence shell of electrons. But instead of those electrons being transferred, they're actually going to be shared as part of each of those atoms' valence shells. So as shown here at the top on the right, we have hydrogen, or H2. So each hydrogen itself only has one valence electron. So together, if they share each of their electrons, they both now have two valence electrons. So hydrogen H2, or this hydrogen gas, now is stable. So if you had like an environment where there was hydrogen with one valence electron just kind of floating around, they would want to link up together to form covalent bonds, because this is how they're going to be stable and have that outer valence shell fulfilled. So that's an example also to show that covalent bonds can form between atoms of the same element, because it's H and H, hydrogen and hydrogen. You could also look at oxygen and oxygen, or nitrogen and nitrogen, which if you hop down to the last bullet point, you can see that it gets a little complex with the formation of double and triple bonds with molecular oxygen and nitrogen, but still these are examples of covalent bonds and covalent compounds. Covalent bonds can also form between atoms of different elements, like shown here, H2O, water. Oxygen has 6 valence electrons by itself, and hydrogen again has 1. So if the oxygen is sharing 1 electron with 2 hydrogens, now oxygen has a full valence shell of 8 electrons, and each of the hydrogens also now have 2. So water in this state is relatively stable. Now, since we can see a couple examples here of how covalent bonds can form between atoms of the same or different elements, there is a property that results from one or the other of these situations, and it has to do with the electronegativity of the atoms that are involved in the formation of the bond. Electronegativity, think of it like how likely an atom of an element is likely to pull electrons towards it. It's sharing the electrons, but some of the elements are can pull stronger on those electrons compared to others. So there's a trend in the periodic table where the more electronegative atoms, more electronegative elements, let's say, are at the top right, excluding group 8, because remember, they're stable. They already have 8 valence electrons. They don't want any more, so that's chopped off this chart. So you're seeing here group 7. So fluorine, which is the smallest element in group 7, is the most electronegative element that exists. And the numbers below the chemical symbols are their electronegativity values. So next will be oxygen, followed by chlorine and nitrogen, sulfur, and so forth. So you get an idea. It's just, you don't have to memorize those numbers, but just understand the trend there with the periodic table and electronegativity. So how does this relate to covalent bonds? Why is this important? When you have 2 elements of the same type of atom sharing electrons, you're going to get what's called a nonpolar covalent bond, because they're the same. they're not competing for those electrons. Like one isn't like more electronegative than the other. They're exactly the same in terms of their electronegativity. So there's more of a symmetrical structure there with respect to where those electrons are found. So you can see that in the chlorine Cl2 example at the top right. That gray bubble kind of represents the electron cloud, and it looks perfectly symmetrical. So that's a nonpolar compound held together by nonpolar covalent bonds. The opposite would be true when you have elements, different elements that are sharing those electrons with different values of electronegativity, like water. In water, oxygen is much more electronegative than hydrogen. How do I know that? Well, let's again look back at the table. So oxygen right next to fluorine is the second most electronegative element. Hydrogen's 2.1, oxygen's 3.5. So again, that means that the electrons that are being shared in this compound are going to be attracted more to the oxygen. So this results in polar covalent bonds, but more importantly, it causes this polarity of the molecule overall, where the oxygen side of water will have a slightly more negative charge. That's that symbol at the top above oxygen. It's actually the Greek letter del and a negative sign, which means partial negative charge. Whereas the hydrogen sides of the water molecule have a slight positive charge. This polarity leads to the third type of bonding called hydrogen bonding. Hydrogen bonds are the weakest type of bonds that we will discuss. It's actually more of an electrostatic attraction between two molecules that have slight positive and slight negative charges because they're polar. Usually you'll see these bonds forming between oxygen and or nitrogen atoms. Here's an example showing water molecule with ammonia, where the hydrogen side of the water is attracted to the nitrogen side of the ammonia, where you see the slight positive linking up with the slight negative. That's a hydrogen bond. Now, these bonds are temporary. They can easily form and be broken, but they do still play an important role in shaping molecules like proteins, which we'll get to more in a later chapter, and also adhering molecules together and allowing for processes to occur in a living thing. Like we'll see the role of this in the process of photosynthesis, water transport, and in fact, the emergent properties of water, which is our next topic, is because of the hydrogen bonds that form between water molecules. So we'll leave it at that for today and get to the emergent properties of water in our next lesson for chapter 2.